So now that you've got the basics of how to set up RStudio, we're ready to use it to start analyzing our data. So the first task we have is we have our data. I'm assuming that you have your data that you've recorded from a fluorimeter. We're going to be working with the calibration data. So this is not enzyme activity data. This is just the how the fluorimeter responds to different concentrations of fluorophore. I assume that you've got those data points written down in a notebook. So the first challenge you have is to get the data from your notebook into R's memory. And there's two ways to do that. The first way is that we could type it in. If we type in data to R, we need to, first of all, save our data as a variable name. Let's call it, creatively, data. So at the command line, I'm going to type in the name of the variable that we want, and then I'm going to type in the assignment operator, which is this sort of less than sign and then a dash, and if you put it together it looks like an arrow. And then we're going to use the concatenate operator. I'm using a lot of words that you might not be familiar with here, but it'll, I think, start to make sense a little bit later. And we actually type in our data values that we have right here. Let's say they were, I don't know, 218 first, and then 528, and then 1,050, 1,033, or whatever. And then if we press enter, you can see in the workspace that there is now a variable called data. So this is a workable way to get data into R, and it's useful in some cases. But there's two reasons that it's not the best way. The first reason is that it's really inconvenient to type in all of your data at the command line. We'd really kind of prefer not to do that. And the second way is that if we do this at the command line, then as soon as we erase the memory in R, then our data is all gone. And this is actually, I'm going to show you how to do this right now because it's very important to know how to erase the memory. We'll do it lots later. And it's a very unintuitive command. The command is rm parentheses list equals ls parentheses, and our data are gone. So like I said, typing all your data in at the command line is not the most effective way to do things. A better way to get data in is to save your data in a file in some other, to get your data into a data file in some other way, and then just import the data directly into R. And that's actually what I usually do. What I usually do is I use Microsoft Excel, which I think is not a very good tool for analyzing data, but it's a pretty solid tool for entering data by hand. I type that in, and then I save the data as what's called a CSV file, and then I import that CSV file into R. So there's a couple of important things. First of all, your data for a calibration curve basically has two variables. It has the volume of standard that you put in, so I've named that variable amc.volume.ul, and it has the actual fluorescence value that went with that volume of standard. And so I've made up some data here. I've said that we put in 0, 10, 50, 75, and 100 microliters of AMC standard. And I got a few of these values from Mr. Murray. And I said the fluorescence values are 218, 1186, 6345, 8512, and 12,840. The important points here are that the names of the columns, each column should have one type of data in it. The names of the columns should be on the first row, and the names of the columns in general shouldn't have any kind of strange characters or spaces in them, and they shouldn't start with a number. The easiest way to think about that is you should just keep your names of your columns pretty simple. You'll notice that instead of using spaces up here, I used periods in between AMC and volume and UL. And then the last thing is that the data should always be in columns rather than in rows. So we've got this data entered, and I'm going to save it as what's called a CSV file. Stands for comma separated values. So we just go in Excel, we go to File and Save As, and like I said, I think it's a little bit different on a PC, but it's the same idea. And then we're going to save it in the same directory, in the same folder that your that is storing your project for RStudio. So again, on my system, I'm keeping this in a directory called Malcolm X, and I'll save it as, let's see, test data. And notice that it says XLS here. I don't want to save it as an XLS format. I want to save it as a CSV format. And there will be a little warning that looks like this, for me at least. It says contains features that will not work, and what that just means is that a CSV is a very simple format that contains only text. So if we made any graphs or we did any other fancy formatting things in Excel, that those changes would be lost, and that's just fine. The other thing is that a CSV file can only contain one worksheet. So if we had an Excel file with multiple worksheets, it would only save one at a time. But that's okay, because we're not doing that. So I've got this saved as testdata.csv. And it's in the same directory as my RStudio project is in. And I'm going to close this down. We can say save the changes, blah, blah, blah. Okay. So now we want to read that data into R. So I can say, in the console, I can say data is read, oops. The function is read.csv. And before I do this, let's just point out that in the files window over here, you can look through what files are present, and testdata.csv is listed there, so that's good. Notice that you'll put the file name in quotation marks. Okay, so I do that, and now I have what's called a data frame. Called data, and I can see the contents of that just by typing the name data and pressing enter, and it looks just like what I entered, so that's a good thing. Now again, I'm doing all of this at the console, but really that's not the best way to do things, because if I delete my memory or if I just make a mistake and want to back up, I can't recreate my steps. So as a practical matter, what I actually do when I'm processing data is that when I want to check to see if something works, I work in the console. But when I know that it works, then I take a command from the console and I put it in the script. And so now that that's here, that's not actually doing anything, just sort of sitting there in my script. But remember, if I run it, if I, for instance, clear out the memory, and then run this line of the script, you can see again that it runs that line and reads data into memory from that file. Another nice thing about scripts is that we can put comments in them. So these are what we use to annotate our code. We put little messages to ourselves. R doesn't ever read the comments, and we indicate the comment with this number sign right here, and you can see that anything behind a number sign will turn green, which tells us that it's not being read by R. So I'll say something like, this reads in the data from the CSV file. It's called data. So the next thing we want to do is plot the data, make a graph of the data, and then we want to find the slope of the relationship between fluorescence and the volume of AMC standard that we added. So to do that, we're going to use a package. There's a lot of ways to make graphs in R, actually, but the way that I like best uses a package called ggplot2. So packages in R are sort of like add-ons to the program. So R by itself, this is called base R, can do a number of interesting things. It's a good package. It's a good program. But what makes R really powerful is the fact that lots of different people have written lots of different packages that do all kinds of excellent things. And that really makes R a really incredibly powerful program. So first we have to install the package. You need an internet connection to do that, and we're only going to do it once. And so since we're only doing it once, I'm doing it down in the console. You type install.packages ggplot2 is the name of the package that we want to install. And you can see that R is thinking about that for a little bit, and it's picking a website to download it from, and it's taking a little bit of time to download it, and now it's done, so it's installed it. We can also do that through the packages menu here, and we can go to install.packages and say ggplot2, this time without the quotation marks, and we could say install and make sure that install dependencies is clicked, and that works well too. And like I said, we only need to install a package one time, and then it sits in the on the hard drive of our computer. But every time we run R, every time we open a new session, so basically at the beginning of every day, we have to load the package. We load the package with a command called require. This time you're not going to use the quotation marks, strangely enough. You can also, oddly enough, use the command library, and they do exactly the same thing. I sort of use them interchangeably. So we want to put require ggplot2 at the beginning of our script because we're going to use ggplot2 in the script, and we want it to run every time. Like I said, there's this variable called data that we've read into our memory that contains the data that we recorded. And it is a type of variable called a data frame. So what a data frame is, formally speaking, is a list of vectors. A vector is a one-dimensional string of either numbers or letters. There's a thing in another kind of vector in R called a factor. A data frame is a collection of those. But the way you can think about it is a data frame has columns and rows, and every column in a data frame has to be the same kind of information. It has to be numbers or characters or something like that. But a data frame can contain different columns of different data types. So in this case, both of these columns are numbers, but we could, if we want, put a little description in words as a third column, so each row would have a description, in words of that sample or something like that. But the thing to know about a data frame is generally we want to put different kinds of information in different columns, and then each row represents a different observation. So in this case, each row represents a different sample. And like I said, there's a whole bunch of data structures in R that we can use, but whenever possible, we want to be working from data frames because that's sort of how things are set up to work nicely. So the first thing we want to do is to plot the data. So we're going to use ggplot to do that, and ggplot has kind of some slightly complicated syntax, but it's easy to sort of copy the syntax to make plots that you want. So the way the syntax works is it goes, every plot starts with ggplot, and then the name of the data frame. In this case, the data frame is called data. And then we set the aesthetic values. So on the x-axis, we want x equals amc.volume.ul. And on the y-axis, we want the column fl. So this told R how we're going to arrange the data, but it doesn't actually say how we want to display it. So to do that, we have to add what's called a geom, and we're going to use geom point followed by the parentheses, and that says display these data as points. And I'm going to sort of make this, it's going to show up in our plot window, which is going to be very small, and it may be hard to see when we do this, but if I run these two columns, we have created a plot here, and it has the name of the variable on each axis, and then it has the points in here. So that's pretty good, and it looks like a good calibration curve, which is not surprising because it's based on made-up data. We could also, if we wanted to, tie these together with a line, although I don't usually do something like that for data like this, but just to show you, we can use, sorry, not geom point, but rather geom line. And there's all kinds of other neat things. One really useful thing is that we can create a linear regression based on the data automatically using ggplot. And the way we do that is something called geom smooth. And then we have to tell it the method to smooth the data is LM, or linear model. So if I run this, you see it will plot a line that represents a linear regression of the data, and then this shaded area around the line is what's called the 95% confidence interval for the slope, or rather for the regression. I don't actually usually like to include that on there, so we're going to turn it off by saying SE equals false. So now we've got a line. But the problem is that we would like to know what the actual slope and intercept of the line is. And ggplot isn't going to tell us that. So the way we're going to do that, we're going to find that out, is we're going to make what's called a linear model of the plot. So we'll call it our model. We're going to use the LM function. You may have noticed that a lot of things in R have parentheses after them, so anything that you see with a parentheses after it is a function. And a function is a little small computer program that works sort of like a mathematical function. The idea is that you put in one or several numbers or variables, and you get out some kind of variable, maybe a number, maybe a whole object, who knows. But the point is you put some stuff in, and you get something out of a function. So we're going to say, the way this works is we want to model fluorescence as a function of amc.volume.ul. So this syntax is a little bit strange. Briefly, what goes on the left of the tilde is the independent, or rather, the dependent variable. It's what you usually put on the y-axis of a plot. What goes on the right is the independent variable, usually what goes on the x-axis of the plot. It turns out we can make these a lot more complicated, and we can do multiple models, multiple variables, and so forth. We don't want to mess around with that. But the last thing is that we have to tell it what data we're working from. We are working from the data frame called data equals data. And this is, I've realized I've chosen a confusing name for a variable, so I'm actually going to change this right now. Call it my data. And then we're going to work from data equals my data. So this is, R has just created a linear model for our data frame that was called my data. But it doesn't tell us anything about that. The way to find out about it is we can just type our model, and it'll give us a little bit of information. It'll tell us down here that the call that created it is, this is just what we typed in, is this thing. And it'll say the coefficients are these numbers. So the coefficients of the linear model are the intercept is 35.12 and the slope is 123.09. Annoyingly, it doesn't say what the slope is. It says what the name of the independent variable, and that makes sense when we're doing multi-dimensional plots, which we're never going to do. But for right now, just in your head, when you see the one on the right that has the weird name, which is not intercept, just think of it as the slope, because it is. We can get a little bit more information out of this by typing summary our model, enter, and then we get a whole bunch of information here. Let me open this window up a little bit more so you can see it. So again, we got the call. This is just the command that created the linear model. It tells us a little bit about what the residuals are. The residuals are just the distance from each point to the modeled line. Then it tells us the coefficients. Again, these are the coefficients that we got before. They're 35.1 some, and they're 123 for the slope. And then it also tells us the error on those coefficients. Basically, it's how certain R is that that is the correct value. So we would report this as 35 plus or minus 385, and 123 plus or minus 6. Finally, it's got this, don't worry about the t-value, but the PR is greater than t is what's sometimes called the p-value. And that tells us how sure we are that that number is different from 0. A low number indicates that we're very certain that it's different from 0. So the intercept has a p-value of about 0.93, which is to say, statistically speaking, we can't say that that's different from 0. Whereas the slope, and that, you know, if you look at the plot, this value looks like it's pretty darn close to 0, so that's not surprising. The slope has a p-value that's very small. It's significantly less than 0.05, and in fact it's less than it's R is telling us this is essentially indistinguishable from 0. So what that's saying is that R is very certain to a very high confidence level that the slope is different from 0. And again, that's not surprising. You look at the plot, you say, of course the slope is different from 0. But when people talk about whether something is statistically significant, this is sort of what the p-value is telling us, that this is a statistically significant number. And then finally, sometimes people talk about the r-squared value of a plot, which is basically telling us how much of the variation in the data is explained by this linear model here. And so you look at the you want to look at the adjusted r-squared is just about 0.99, which is to say almost all of the variation in the data is explained by the linear model, which is to say that it's a pretty good linear model. A lot of the work that we're going to be doing is finding the slopes between relationships. So for the calibration curve, it's finding the slope of fluorescence as a function of AMC value, which tells you for 1 microliter of AMC added, how much does the fluorescence increase? And that answer is for 1 microliter of AMC added, fluorescence increases by 123 fluorescence units. And then later on, we're going to be doing enzyme activities where we're saying, in every hour, how much does fluorescence increase as a result of the enzymes that are in our sample? And in both cases, we're looking for the slope of a relationship. So this is how we get the slope of the relationship. And I'll just say real quickly that if we want to actually assign that slope to a variable that's in R, we can use a function called coefficient. So we can say my slope, we'll have a variable called my slope is coefficients I'll type command enter, and that gives us a variable called mySlope. If we type out mySlope down here, it'll tell us. So this is just a vector with the same information, and maybe we want to just look at the slope. So that's the second element of the vector. So we put a 2 in square brackets here, and I'll type command enter again. And mySlope is just this number 123. So this is the first task, is to take the calibration curve that I believe that you all have made and figure out what the slope of it is as a function of the volume of AMC that you've put in.